Hey guys, today we are looking at our notes for 3.4 Part 1, Introduction to Linear Programming. So linear programming is a way for us to take a bunch of different what's called constraints and be able to see how they interact with each other in a system. So it's an extension of what we talked about yesterday with 3.3 being our system of inequalities. It is just a specialized version of that along with that system of inequalities, we have a bunch of different what's called constraints that are equivalent to our inequalities, but we have an overarching function that might be analyzing some interaction of our x and our y values. So for today, what we're focused in on is just going back to graphing that system of inequalities, finding our intersection points between them. Those are going to be called our vertices. That is the corners of our what's called the feasible region, to be able to find where our kind of max and min values are. Okay, so our constraint is just one of our inequalities in that linear system, that linear programming problem. Our objective function is, again, that overarching equation function that is trying to maximize or minimize a certain value. And then those vertices are just those points where my inequalities intersect each other. So that feasible region is that kind of shaded area where all of my inequalities overlap each other. And we're trying to find the vertices of those things. So our objective equation here, our objective function will be given to us as an f of x comma y function, because again, we're dealing with two variable inequalities that are going to be x and y values. We're going to be measuring some different things tomorrow with our word problems, where they'll represent different things, maybe tickets and stuff. So like, again, similar to other word problems, but for right now, we're just focused on what does that look like. So it could be something where, we're just looking at some different measurement of our x and y values. So maybe like 40x minus, 15y. And that's going to be our equation that tells us how we are looking at our sales totals or our different things that we're trying to either maximize the value of this thing or minimize the cost of this thing. Okay, so for this first example, this is just what a graph could possibly look like for our linear programming problems. So we're not limited to just two inequalities. There have been three of them that we saw for that last problem in our notes yesterday. This one has four different inequalities that we are graphed, or that have been graphed for us, where this shaded area here that I'll highlight in yellow just to kind of bring it to our attention because it doesn't look super dark on my screen at least. That area is the feasible region. So that shaded area represents all the different possibilities that fit our constraints. So we've got all these different limitations that we might be measuring in this particular problem, maybe sourcing issues, cost variables, time that we have available for workers and stuff for these different kind of problems. But all of these different data points fit within our constraints. So if we're trying to maximize or minimize a different cost or value, we're going to be given the function for that. The objective function is the thing that tells us what our max and our mins happen at, like what we're measuring at. So what we have to do for this to maximize the value, we are going to take those vertices, which are the corners of my feasible region. In this case, I have four of them, four corners. Since it's a quadrilateral, we've got four sides. Those points at the very edges of our feasible region are going to be the places where our maximum or minimum values happen. That is always the case. You're not going to have something in the middle here that maximizes or minimizes because it's not at the very, very edge of that shaded area. The very edges give us either those max or min values. Okay, now, in example number one, we're trying to maximize this function. So we're going to plug in our different coordinates to that equation to find what their individual values are. So our 4 points that we're going to be measuring are 0, 4. That's our kind of top middle corner. We've got 0, 6. Oh, sorry, 2, 6. 2 comma 6. Nope, I'm 2 comma 4. Still at positive 4 for my y value. 2 comma 4. Over here we got 5 comma 1. And then -1, -2, -1, -2. Right, those are my 4 coordinates. And so if I plug those x and y values into my objective function, it's going to give me the value at that point for our objective. So plugging in 0 for my x value and 4 for my y value gives me 25 times 0 plus, I'm going to have to leave myself some more space here, but that's okay, plus 30 times 4 So 0 plus 120, which gives me 120. I'm going to have to move this one, I think. So let's go ahead and scoot this on over. For 2 comma 4, that would be 25 times 2 plus 30 times 4, which would be 50 plus 120, so 170. For negative 1, negative 2, we've got 25 times negative 1, 25 times negative 1, plus 30 times negative 2, gives me negative 25 minus 60, so negative 85. And then our last one, I'm going to have to rewrite here at the bottom, was 5 comma 1. And that would have been 25 times 5 plus 30 times 1, which would be, 25 would be 125 plus 30, so 155. So now that I've got my values for each of those different vertices, I can look to see which one of those gives me the highest output for our objective function, which 170 is the biggest output that we have. So 2 comma 4 is the maximum, the point where the maximum happens, but 170 is the maximum of that value. So again, depending on how the question is phrased for you, if you want to know what are the x and y values, what is the point of your max value, that would be 2 comma 4. In this case, they want us to maximize the objective function. 170 is the max output of that objective function. Okay, but otherwise, just graphing our inequalities, finding those vertices, plugging into our points to either find the max or the min. Okay, so for example number 2, we're asked to graph the feasible region using the following constraints. So now we're given 4 different inequalities that we're going to have to graph and find what that feasible region looks like before I can do any kind of equation manipulation with them. Okay, so I want to go ahead and just start with our easy ones, right? These top 2 ones are just putting us in quadrant 1, right? X is greater than or equal to 0. That is just a vertical line at 0. Y is greater than or equal to 0 is just a horizontal line at 0. So that kind of puts us in quadrant 1 territory. My kind of next equation here, this one is positive 3 for my y-intercept. 1, 2, 3 is that point right there. And then my slope is 3, so 1, 2, 3 over 1. 1, 2, 3, that's off the graph, so we're going to go, that's it. All right, so we're going to go right here. I can extend my line back the other way for myself. There we go. And then y is less than or equal to negative x plus 7. That would be up 1, 2, 3, 4, 5, 6, 7. And down 1, right 1 would be in that direction there. Let me go ahead and just make sure. There we go. So it should be down 1, right 1, down 1, right 1. Yes, right here. Okay, so now in this case, I've got those graphed. My feasible region, I am greater than each of my 2 vertical and horizontal lines, but then less than my 2 angled ones, less than or equal to in all of these. So my feasible region would be this area bound by all of them. Now you can double check to make sure that that is the case. Based on your inequalities, that should still match up correctly. But once you have all of them graphed, kind of the area that is bound by all of those values is going to be where that vertex, like where your feasible region is. Okay, so that would be all to do for this one. We don't have to identify or describe what those vertices are for this point. They just want us to graph the feasible region, and that would be good. That would be all that we need to do for that problem. Now, number 3, example 3 here, that we're going to finish off with, does continue using that same thing. They want us to minimize and maximize the objective function f of x being equal to 10x plus 16. So we need to know what our vertices are first, and then we can plug those into our objective function to be able to find our different values to maximize or minimize. Okay, so looking back at my coordinates here, my intersection points happen, I've got one of them at 0, 0. I have one of them at 0, 3. I have one of them over here at 1, 6. And then the one all the way far to the right happens at 7, 0. Okay, so those are my 4 different vertices for my feasible region. So since I'm trying to maximize and minimize the equation 10x plus 16y, I'm going to plug in my x and my y values to each of those 3, or sorry, each of those 4, to be able to find what the max value is and what the min value is. So we've got, we'll do this in red. So 10 times 0 plus 16 times 0 is 0. Cool. 10 times 0 plus 16 times 3 is 48. 10 times 1 plus 16 times 6. I'll clean that up a little bit. 16 times 6 gives me 106. And then 10 times 7 plus 16 times 0 gives me 70. Okay. So now that I have all 4 of those different outputs, I know that my maximum value is 106. That happened at the point 1, 6. My minimum value was 0, and that happened at 0, 0. Right, you don't have to include the at part. My solution's maximum value is 106. My minimum value is 0 is good enough. That's all they really ask for here. They don't want us to just maximize and minimize the 2 values. So that is just what is the lowest output that is possible of any point on your feasible region based on the objective function, and what is the maximum value of your feasible region of any of the coordinates based on the objective function. If they wanted to know where the max happens, 1, 6. If they wanted to know where the minimum happens, 0, 0. Which should make sense. Like if we're trying to minimize our values, if we're looking at it as a coordinate, like in our picture, our minimums are going to happen all the way as far left and down as we want to, as we can possibly do. Our maximum value should happen farthest up and to the right as possible. So really it should have been, like our minimum value should have been obvious. 0, 0 is going to not give us anything for our outputs. But looking between our 2 kind of high up and far right points, you really should be focused more in on those when we're looking for our max values, because that should be where we expect it to happen, right? It's just trying to figure out, based on what the equation is a bigger x value or bigger y value to be more impactful for our particular ones. But that's all I got for us for today. It's really just those 2, just getting us used to graphing those feasible regions, finding our different vertices, and then either maximizing or minimizing some different points. So for your homework tonight, you are just working on page 132 and 133, 3 through 7, and then 15 through 29 odds, just to get used to those types of problems. Tomorrow, we'll come back to day 2 of 3.4, where we'll start incorporating word problems to be able to set up some of those different feasible regions and have some applications to them so you can kind of see what that would look like in a real world problem. So as always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and let me know. And have a fantastic day. We'll see you soon.